Welcome. Let's take a look at optimization and introduce the idea through this numerical example. We're looking for two numbers such that the product of the two numbers is negative 25 and the sum of the squares of the two numbers is a minimum. So let's start by defining those two numbers. So we will let x and y be the two numbers. So let x and y be the two numbers. Now, what do we want to have happen with these two numbers? We want the product to equal negative 25. So the product is going to be p, and if I multiply those two numbers, that's x times y, and we want that to equal negative 25. What else do we want to have happen? We want the sum of the squares of the two numbers to be minimum. So we're going to call s the sum of squares. So our sum of squares, we'll call that s, and that would be the sum, or adding the squares of both numbers. So x squared plus y squared. And it says we want to find the minimum or minimize this quantity. Okay, so if we want to minimize the sum of squares, we will be using calculus, but the challenge here is that the function we want to minimize has two variables, x and y. Now, there are ways to find the derivative of this function and find critical points, but that's beyond the scope of this of Calculus 1. So we need another strategy. Well, we do know that we need the product of the two numbers to be negative 25. So something we could do is a substitution. And basically we could take this relationship x times y equals negative 25, and based on that relationship, if we divide that equation by x on both sides, we'll get y equals negative 25 over x. And we can then replace that y in my sum of squares. So my sum of squares would now be x squared plus negative 25 over x, quantity squared. And by doing that substitution, I have now ensured the relationship that the product of x and y is negative 25, while I will be looking for the minimum of this function. So I've connected these two ideas together, the product and the sum of squares. So again, we want to minimize this, so let's just go one step further with s and say x squared, s is equal to x squared plus 25 squared over x squared, and then 25 squared is 625. So we have s is equal to x squared plus 625 over x squared. And now what we want to do is minimize this function. So here's our function we're working with, and now let's find its derivative so that we can find critical points and determine whether or not we have a maximum or a minimum. So s prime of x is equal to, the derivative of x squared is 2x, And as I'm thinking about taking the derivative of my second term, I will be thinking of that as 625 times x to the negative 2 power. So that when I do the derivative, find the derivative here, I will have 625 times negative 2x to the negative 3 power, which then becomes 2x minus 1,250 over x cubed. And so now we need to find critical points. Let's go ahead and get a common denominator for my two terms. That common denominator would be x cubed. So then I need to multiply the 2x by x cubed over x cubed to get that common denominator. And so s prime of x is now equal to 2x to the fourth minus 1,250 all over x cubed. Let's do a little bit with that numerator. Let's factor. So I can factor out a 2, and I'll have x to the fourth minus 625 all over x cubed. Now, as we're looking for critical points, there are two sources. One source is where s prime of x equals 0. And the second source is where s prime of x does not exist. Well, s prime of x does not exist where the derivative, or the denominator of the derivative equals 0. Well, that would be where x equals 0. But in the context of this problem where we want the product of our two numbers to be negative 25, this x equals 0 is not helpful. If one of our numbers is 0, then the product will not be negative 25. So we can disregard that critical point. And let's come back over and consider the first source. That is where the derivative equals 0. Well, if the derivative equals 0, then the numerator will have to be 0. So that means that the x to the fourth minus 625 has to be 0. So I've got x to the fourth minus 625 equals 0. And we saw earlier that 625 is a perfect square. It's 25 squared, so we can factor this as a difference of squares. X to the fourth is x squared times x squared. 25 squared is 625, so one of my factors will be x squared plus 25, and the other factor will be x squared minus 25. And we want that to equal 0. Now we notice that there are no real numbers that will cause x squared plus 25 to equal 0. So we will disregard this factor and focus on x squared minus 25 equaling 0. So we want x squared minus 25 to equal 0. If I add 25 to both sides of the equation, I get x squared equals 25. And then if I take the square root of both sides of that equation, I get x equals plus or minus the square root of 25, which is plus or minus 5. So the only viable critical points that we have for this function are x equals negative 5 and positive 5. Now keep in mind that our goal here was to minimize or find a minimum. So we need to test these values to see if we do in fact have a minimum. So let's go ahead and set up our first derivative test. So we will be testing s prime and we have 2 critical points. So we will have 3 intervals on which to test. We'll have from -infinity up to -5, from -5 onward to 5, and then from 5 to infinity. Okay, so now let's select some test points within each interval. Recall that we're only interested in the sign of the derivative, not its actual value. So in our first interval here, we could try s prime at a number like -10. So s prime at -10 would be, and then we go up here to where we see s prime, we would have 2 times -10 to the 4th power minus 625 over -10 cubed. And so as we look at this, we can tell that our denominator is going to be negative, and our numerator, well, 10 to the 4th power is 1 followed by 4 zeros, so 10,000, and 10,000, and that will be a positive value. 10,000 minus 625 is going to be positive, and then multiply by 2, definitely positive. So on the interval from -infinity to -5, our derivative is negative. Choosing a value in our next interval, say maybe 0, so s at 0 is equal to, and again looking at our derivative here, we will have 2 times 0 to the 4th minus 625 over 0 cubed. And all of a sudden we have a problem. Now, why do we have this problem? Well, the reason we didn't have this problem is while we looked for sources of critical points, we did not attend to the fact that we have a domain restriction in our derivative and also in our original function. We didn't attend to that. So sometimes this will happen. And so this is how we deal with that. We come back, we make sure that we remind ourselves that x cannot equal 0 for both the original function and for the derivative. So that means when I set up my test here, I need to be a little bit more careful. I need to go from -5 to 0, from 0 to 5, and then from 5 to infinity. So we're going to add another box here, and that will allow us to test on the appropriate intervals. So now that we've corrected our oversight, we can continue with testing. So now the appropriate interval is -5 to 0, and let's choose -1. That's a nice, easy number to work with. So s prime at -1 is 2 times -1 to the 4th power minus 625 over -1 cubed. So we can see that our denominator, again, we have a negative number cubed, so that will be negative. And in our numerator, we have +2 times what happens in these parentheses. Raising -1 to the 4th power is a +1 minus 625. That's going to end up giving us a negative quantity in our numerator. So we have a negative number divided by a negative number, which tells us that the derivative is positive on the interval from -5 to 0. Moving on from 0 to 5, let's test s prime at 1. So we'll have 2 times 1 to the 4th minus 625, all divided by 2 times 1 cubed. Our denominator here is positive, and there's no 2 in that denominator. My apologies. 1 cubed is positive, In our numerator, we're having a similar situation as at -1. So our numerator is negative, which means our derivative is negative on the interval from 0 to 5. Lastly, let's check our interval from 5 to infinity. We could use 10 to do that. So we'll have 2 times the quantity, and we have 10 to the 4th minus 625, all divided by 10 cubed. Our denominator is positive, and our numerator, in much the same way our numerator at -10 was positive, our numerator at +10 is positive. So we have a positive number divided by a positive number, which means that the derivative is positive on this interval. So with that in mind, we can say that the function s is decreasing on the interval from -infinity to -5, then increasing from -5 to 0. Recall that we have this domain restriction at 0, x cannot equal 0. Then decreasing on the interval from 0 to 5, and then increasing from 5 onward. So it appears that we have 2 possible minimums, one being at x equals -5, we have a minimum, and the other being at x equals 5. We have minimums at both locations. So we have 2 solutions. So we can say if x equals -5, then, and we come back here to where we said y was equal to -25 over x, y equals -25 over -5, which is 5. And we can also say that if x equals +5, then y equals -25 over +5, which is -5. So what this tells us is that for those 2 numbers, one of the numbers must be +5 and the other -5, regardless of whether we call x 5 or y 5. If x is 5, y is -5. If y is 5, then x is -5. So I want to close this video with a general strategy for solving optimization problems. When you're faced with problems such as the one we just did, we want to be sure to introduce and define all variables. Also include a drawing with the variables labeled. In this case, a drawing was not suitable, but there are many optimization problems for which it is. We want to clearly define the quantity being maximized or minimized, and for what range of values or variables this can be done. Note that we had that issue with a critical point at x equals 0, and then discovering later on that 0 was not even in the domain. So we want to attend to that. Write a formula for the quantity being maximized or minimized. Often we refer to this as the objective function. Then we want to write any equations relating to the independent variables or the variables that we use in our formula. And this is also often referred to as the constraint. Now, not always are you going to have one constraint, but this is just a general strategy. But we're going to use those constraints to rewrite the objective function as a function of a single variable. That's the key. We want to create a function that is a function of a single variable. Then we'll go ahead and use calculus to locate the maximum or minimum value of that function. And we'll take into consideration the domain within the situation or the context. We will apply appropriate tests to confirm the classification of the maximum or the minimum. I hope you find this helpful.